Okay. So basically here is, I just showed in the left, you can see this is a computer in 1956, a 5 megabyte computer from IBM. It weighs tons, it's 2 meters square. It's a huge one. And you can see to the right side is a 1 terabyte memory for $20 in eBay, 200,000 times more in capacity. And so the conclusion here, the only things constant in life is change. So it doesn't matter what we do. The only thing that is constant and will continue to do is changing. So we have to be always ready to change. What happened through life is we always look at cycle of life, things that come in cycle from when Earth got created to today. What we see is how does new technologies, new revolutions comes in. They tend to impact people. In the past, it impacts a very small number, and it lasts for a long time. It goes for 500 years, the same technologies. And it seems like lately things are getting, it impacts more people for a shorter time, is getting shorter and shorter, and technologies are coming and going at a very, very high speed. So I'm gonna focus my talk on, especially on the Industrial Revolution, and there are 4 of them. For those who are not familiar with them, I'm gonna go and let me know if I'm going too fast, or you want me to stop on something I can explain. I'll go, what is the first Industrial Revolutions? The first Industrial Revolution came in 1784. It's purely based on steam, that time when people figure out how to use an engine with steam and water, and were able to use mechanical production equipment and all these. So there is, around this technology, there is a huge industry revolution that came in and changed the way things are done in the world. It got followed by the second Industrial Revolution, which came in 1870, about 100 years later. And here comes the electricity that took over the steam engine. And it was recognized by the division of labor, that the people that do specific things, they work together. People that do cotton, they go and do cotton. People that do agriculture, so there is a division of labor, and electricity was the work, and there is a production of masses. That's what characterized the second Industrial Revolution. You see, until 1969, and you see that it's getting to be a little bit faster. In 1969, what comes in was the electronics, took over from electricity. And the IT came in, and the automation. So the automation of making cars, of making this, of making that, computer, making everything. And in fact, most of you probably were not there in 1960. In the 70s, there's at the beginning of the third Industrial Revolution, people were so afraid that the machine will take over, and we'll lose our job, and everything will be automated. And it was a big fear. And that fear went on. How it went by is it just people moved on to other stuff. Instead of doing what the machine can do, we do something else, and we learn how to work with the machine, how to program the machine, these things. So people evolve. So we evolve, and that's very important for every revolution. We need to train the workforce. The way we educate the student should be different, and all that. And now, starting 2010, there is this fourth Industrial Revolution. It's not well defined. I will try to give a stab at it. This fourth Industrial Revolution is defined as being the fusion of this cyberspace around us with the physical space. That means the physical space that we know, things around us, but combined with the cyberspace, internet, things around it that make decision for and feed us the information. So we had that fusion is called the And you can see that the definition is not very well because people don't understand it very well at this stage. And what do people think the parameter that will affect this fourth industrial revolution is? IoT is one of the biggest things. AI and machine learning are at the heart of things. There are other things that people are thinking about. It is like 3D printing, autonomous objects like Hoyas Samir was talking about, virtual reality that's going to come and change things, nano and bioengineering, how we can change, how do we do diagnostics, how do we cure people, how do we predict medications. And one important thing with all these, unfortunately, we'll be giving our lives and giving our information to this, to the outside world. So security become the key player. For all this to work, you need 5G and beyond. What is 5G? 5G is like 4G, like 3G, like anything. It's a platform that slightly different than the other one, is capable to run at a very low latency, where people that, for example, you should have a response to an autonomous object in less than a millisecond, and capable to interact with all the IoTs that are located around us. Those are the two main ones. Of course, it runs at a very high frequency, but that's and high bandwidth, but the key ones is interacting with the IoT around us and interacting with the autonomous objects around us. Okay, come on, move. Okay, so if we look in the whole image, what are we after? The customers, if you ask the customer, what do you, anybody of us in the street from the past to today, they want only one thing. They want information here, they want it now, and they want it for free. Those are the three things that we want. I want to listen, I want to watch my Facebook, I want to watch TV, I want to do this, I do that, and I'll be able to do them wherever I want and for free. So it started a while back with the phone. Unfortunately, the phone has a cord, so you are tied to the house only. You can do it only in the house. So that was a limiting factor. Then we moved, the wireless comes in, and it become easier, so that I can talk to anybody. They can get information to my phone. And the only problem now, what is the bandwidth? The bandwidth is limited between me and my phone connected to the outside. So there is how fast can I type on the phone, and how much information my phone give me. So that's become the limiting factor. The fourth industrial revolution to the right, what you see it here. And this one, basically, imagine yourself, here I have to describe it a little bit different. In the past, we are standing and we are connected to something through a cord, wireless or wired. Now, we are like living inside a computer. Ourselves, we walk, and there is all these IoTs and these machine autonomous things around us that's making, taking information, making decision, and feeding us information. So we are in the middle of the whole thing. So the surrounding around us that take the decision, and that's what. Let's look at computing through history, how it's gone. In the 40s, computing is nothing that me giving the machine numbers, it's computed, it does multiplication or division or whatever, and it feeds me the data back. That's it. It does an operation and give it to me back. In the 50s, people become smarter and they say, oh, no, this does not work very well. Let's give the machine some algorithm and we'll tell it, if you get this thing, do this. If you multiply it, if you see this guy, do this thing. So we start giving it more knowledge and more instruction, and we gave it a machine to store. So that's what happened in the 50s. What's happening today, what's going to happen today is the machine itself It can do the programming, it can do basically the learning, and it can learn by itself. We don't have to tell it what to do. And it takes decision and it feeds us the decision afterward by itself. So that's how the progression is going. So I'm not going to go in detail on these things. I call it the invasion of the machine. So basically from driverless car, the top one, that's me in Waymo Google car. You are all familiar with the autonomous car, virtual realities everywhere, being able to see things in virtual, combine it and being able to fix things, to adjust things, to monitor stuff. So I'm not going to elaborate since I'm going to talk about the electronic behind it. The second one is we have birds that even get fooled by other birds that are mechanical. We have machines that are going to be used in armies. We have insects that are going to be used in agriculture. We have to the right one, it's an interesting one because I was in the hospital a few years ago and I had a robot came to the office. I freaked out. So we're going to have a robot that deliver things and do things. So far, they don't do injection, but they can do a lot of mundane and routine things. As far as robots, like Samir talked early on, I mean, from delivering pizza, I don't know who wants his pizza delivered by a robot, but it does exist, to ambulances, to security guiding pipelines, to agriculture, spraying, monitoring agriculture, to even to the lower side. I like the lower side is they have an injection attached to the to a robot, and that's they found it very useful if you have goats and sheep and cows in the field and you want to inject them and you don't want to have to bring them. So this drone run to them and give them the injection and come back. So it's minimized and it's Samir has talked about diagnostics. It's very famous that people can diagnose. In fact, there's a huge problem that exists today that people are capable to diagnose cancer 4 years before the doctor are able to, 4 to 5 years before the doctors are able to see the cancer itself. So it becomes creating ethical problems. Who decide who is sick? Is it the machine or the doctor? And this is creating an ethical problems. To the right, people are able to diagnose looking at diseases. I'm not going to elaborate much since that's not what I'm trying to talk about today. Anyway, so we go back to performance. If you look through the time, and this is a slide from Intel, a long time ago in the 80s, it was digitizing everything. At that time, we want to digitize everything. Then we said, oh, came the wave where network everything. Then then came to mobile everything. Everything goes to a mobile. Everything is connected. Everything, we do everything on a mobile. And you know, in the last few years, it has been cloud everything. Everybody you talk to is sent to the cloud, go to the cloud, everything cloud. Now we are going to everything to the interconnected devices, and it's expected, they call it intelligence everything. And that's what AI plays a big role, because now we need an intelligence behind every devices. And it's expected that to be around 100 billion intelligent connected devices surrounding us very soon. And you can see from a data point of view, the amount of data that's growing is going exponential. In fact, by 2025, we're expecting to have 175 zettabytes. When I hear zettabyte, for me, it's a big number. For those who do not know what a zettabyte is, I think it's a 1 and 21 zeros behind it. So you can imagine it's absolutely a huge number. So probably for a software engineer, they don't care. It's number, they're gonna manage it. For hardware engineer like myself, it's a headache. So, and what happened is, it turned out that data today, to be stored, it's about double every 2 to 3 years the amount of data that needs to be stored. So not only you have to find where to store it, but you have to store it faster and faster and faster. So those machines are is becoming the technology behind it. The technology that exists today is not good enough to do the work. So from an electronic point of view, now I'm going to switch it from an electronic point of view. All this mobile computing, smart home, artificial intelligence, virtual reality, whatever you can call it, all this data is going to go to a chip somewhere. And now that chip has to be able to handle these things. And now I'm going to talk about what happened inside that chip and what are the problems that people are trying to solve. To go there, I have to lead you a little bit to something called Moore's Law. I don't know whether you are familiar or not. Moore's Law, Mr. Moore is the founder of Intel. And there is a law, even though it is not a law, it's an observation only, but it's known as Moore's Law. It's one of the most famous law in the universe. Basically, every chip will double in capacity or shrink in size, whatever you can call it, every 2 years. It used to be 3 years, 2 years. It gets double the amount of information transistor in it. And this has been going on forever. Everybody is thinking that we are reaching the level where this this thing cannot continue forever. And I will come to why is that. If you have done any electronics in life, you will know that all the electronics up to today, on the wafers or in chip, they are all made on a surface. They are made on a 2D surface, which means basically you have a wafer, you put your transistor in one layer and that's it. So all the electronics up to today. To the left, you're going to see that an IBM 2 nanometers wafer that was just announced this week. That's the, and I'll come to it. What is 2 nanometer? 2 nanometer is basically when we do a chip, we make the design inside, we have to draw lines and transistor and all these, is the feature that we form. So in 2001, we used to do 130 nanometers features. And every couple of years, every 2 years, you can see it's dropping, getting smaller and smaller and smaller and smaller. And today we're reaching a 2 nanometers. In fact, we're beating the law of physics. It's getting so hard to make, to the point that it used to be so many companies that are making electronic, they all quit and they dropped it. And there are left only few companies in the world that are capable to do this level of transistor. So everybody is left the field. And that's because making electronic is, you need a fab that is about $10 billion to $20 billion. And not many people have that much money. There are left only few people who can do it. So this is driving the electronic to a limit where you cannot go beyond 2 nanometers. The second thing is the chip itself. People, why do we go to smaller and smaller and smaller? For the simple reason is we make more and make it cheaper. So the more transistor we make by unit area, the price goes down and it's consumed less power. So people are happy. They are buying computer as cheaper, buying a phone as cheaper. And that is reaching at 5 nanometer, 2 nanometer. The price per unit area is going up, starting to go up, and it's not benefit. So what are the three main problem bottleneck in technologies? So I'm going to describe them as they are here. There are three sections. It's within the transistor itself, within the chip itself. The chip itself is how fast can you process the data within the chip? That is a key. How can we make the chip go faster and faster or increase bandwidth? And it turned out as the feature gets smaller, you have problems. The second one is, even you have processed this chip, you still have to deliver it to the next chip or to the next memory. That's why the red line I showed, the red line is the communication between chip on a board. And that communication is a huge bottleneck. The third one is, even if I communicate and I get all this data, where do I store it? How far it is, how much storage do I need? Those are the three biggest nightmare for somebody who is in the hardware like myself think about. In the chip, when I said early on, then this is the new technology that did not show up yet. It's not in the market yet, but that's what you're going to see in the next few years, and it's going to overtake technology. I told you the chip is done in one dimension only, in a surface only. So here, the chip in the future, they're going to be stacked on top of each other. And because within the chip, it's becoming very hard to talk within the chip. So it's easier to talk from chip to chip, going vertically and talking to the chip. And having many chips to talk to each other, you increase the bandwidth, you lower the power, and you create a lot of things. You create a whole system within one chip. And this technology is called hybrid interconnect, and it's going to be in the market. It is a huge impact in the industry. The second one is how to move data from, especially for AI. The biggest problem is how to move the data from a GPU to the memory, because you process all this data and you're going back and forth to the dumping all this information to the bringing more data from the for the memory to the GPU or the CPU, and processing it, sending it back, then bringing more data. And for an AI person, there is no limit to how much bandwidth they want. They need as much bandwidth as possible. If you can give them a flood, they will tell you not enough. So the biggest problem for us is, how do we bring the GPU, as you see it here, and we have to bring it to the memory that all stacks on top of each other, and creating this communication, this very fast communication between the two. And here, in fact, this cross section is this red line cut. This is the most advanced GPUs that you can find in the market. It's called like if you go to NVIDIA and check their latest ones, this is NVIDIA. There are a few other people that do theirs, and they have 4 stacks. This one stack, and this is another stack. There are 4 stacks. They call them HBM, and HBM stands for high bandwidth memory. And this is a cross section. I don't think you are interested to see this. Okay, so, and I will come back. I wrote at the bottom this. These GPUs can deliver 1.5 terabytes per second. I will come back to explain what this one is. The third one is memory. If you do all that, but still we want to store in memory, especially flash drives for us and all that stuff. How can we flash? So like we use in our flash, we have only one layer of transistors per flash. So nowadays the technology has developed where people are able to stack and make a really 3-dimension stack of memory that can go, some people have gone all the way to 256 layers, which means you stack this layer, and each one of them will give you what you get in the past. So you get 256 layers, the times the capacities, and a faster bandwidth. And if you take these and you stack them on top of each other, which will happen in the future, then you can have in the zettabyte of information stored in your system. So I will jump into. I'm going to go back to these GPUs that are what's used in processing, and I will tell you something. Before this technology was started a long time ago, I worked at Google, so a lot of people know I worked at Google for some time, and this was my first job, creating this first Google GPU 1 and GPU 2. So at Google at that time, if everybody in the world talked for 3 minutes on their phone, voice, they would have crashed Google's systems, because there is not enough bandwidth that can handle the processing. And if you look at the first trial when we did the first GPU, GPU stands for Tensor Processing Unit of Google. This is the GPU here. And you look at it's the traditional way of making memories. You put all the memory in one side and all the memory in one side. And so this will give you a DDR3 SDRAM running at 2100 megahertz. And those are two channels. This is one channel, so it's talking to one channel. And this one is talking to the second channel. And all in all, that can deliver a 34 gigabytes per second. That's maximum. And this is the data center. In fact, this data center was the system I worked on. So you can see, and you stack a bunch of those on top of each other, and you create your system. This is supposed, when it came out, it was supposed to be in 2015. It was the biggest thing. It's called a sliced bread, and it delivered 34 gigabytes per card. I call it per module if you want to see. Then after that, we developed, we went and said, no, this is not enough, because the AI guys like, this is not enough for me, give me more. So by going more, so we jumped to GPU2 design, and the GPU2 design, and I will come back and show you how it is. We increased the bandwidth to 600 gigabytes of performance, that's 45 teraflops. And they put 4 of those GPUs on one modules, and using a 2.4 terabytes per chip. And we put a bunch of them in a module that'll end up as 64 of them, of this module assembled together in one rack. And that gives you to 11.5 terabyte petaflops. Anyway, the GPU2, when it came out only 2 years after that, it was 70 times X the bandwidth of the GPU1. And this is how it was done. So basically, instead of relying on the old technology that I told you, where you use one GPUs and you surround it with 2 channels of all memory sitting, now we went and we put the GPU in the middle, we put all these ISBM that are stacked, and we bring them as close as possible, and then we put each one of them here. So, and we put 4 of them that talk to each other, and each one of them has its own memory. And this cable is, I will show you where this yellow one were cable. But look at what's interesting here on the top of it. This gets extremely hot. So we put, they're water cooled. So we have a metal thing here, and the water comes in. It cools this one, and it goes to the other one, it comes back. This is a cooling system. And you can see it in more better here, the water cooling. Then you put these racks, you put them here, you stack them, a bunch of them, then they become one unit rack. unit, then each one of them is stacked into the in the rack itself, and they're all connected to create what they call a circular system. So the within each module you have GPU and 4 memories surrounding it, and they're 4 talking to each other, and those they become 16 and they make a circular. So basically they are, you can imagine it's all designed for an AI application where the data is shared between all the GPUs to process the data. Just how this is the GPUs, this is how it looks, and just want to show you. And the difference here is the connection between the GPUs and the memory. Instead of becoming 64 bits, it's 1024 bits per channel, and each one of them is going as 3.2 gigabits. This is what exists today in the high and state of the art. I mean, if you can get those, but still people are saying this is not enough. Move us forward. So what's coming is a technology that we are working on. It's called a hybrid interconnect, where the chip are completely connected to each other, but they create an amazing number of interconnects between each other, such a way that the bandwidth is going to explode, and that's what we are hoping for. So this technology is just in the working. At least with my group, we're doing quite a bit of work on it. So be ready for an HBM3 and HBM4 that will lead us to even higher bandwidth for you guys. And my closing statement is going to be, if you look at this paper, it came in 1953. If you look at, this is the president of Pacific Bell telephone company. And look what he said here. Talking about the future, this is in 1953, he says, in its final development, the telephone will be carried about by an individual, perhaps as we carry a watch today. It is probably will require no dialing or equivalent, and I think the user will be able to see each other if they want as they talk to each other. Who knows? But what it may actually translate from one language to another. This is for me, so I decided, okay, let me give it a prediction what will happen in 70 years from now. So don't take it with a grain of salt. So you'll be all happy to know there are going to be no phones and no laptops. So I believe intelligent information will be received to us directly, orally, or visually, and maybe through thoughts. And thank you.